Okay, so I want to look at a constructing in two dimensions only today. One of those problems with you. There are a lot like this that you have probably seen before in Algebra 2 where you have like a piece of paper and you have to have certain margins and you're trying to maximize the printing area or something like that. And I think those ones are much more straightforward. So I wanted to go over one like this with you. It's an inscribing problem where you are constructing a shape that has to be inscribed usually under some graph. And the trick to these is that you have to use the graph to help to define the dimensions of the shape, right? So in this particular case, we have a rectangle that is to be inscribed under one arc of the sine curve. So in this graph, they show us the arc of the sine curve. So we know this is 0 and we know this is pi. So we know, regardless of which arc this distance here is going to be pi. We know that. And we also know that this graph is symmetrical, right? So if I put a rectangle under here, and this is just one example of a rectangle, right? I could inscribe a rectangle that's really short but long. I could inscribe a rectangle in here that's in the middle, that's tall and thin. What I'm not going to be able to do is inscribe a rectangle that isn't symmetrical in here, right? Like if I try to do a rectangle that goes from here to here, it's not going to be a rectangle. It's going to be a trapezoid. So if I'm inscribing a rectangle, I know there's going to be symmetry involved here. So we're going to use that to our advantage in a big way in this problem. Okay, so again, this is just one random rectangle that we're going to use as a way to define our dimensions, but it could be the corners of the rectangle could be anywhere along this curve. It could be a tall, thin one, it could be a short, fat one, it could be somewhere in between. Okay, so we want to know the largest area the rectangle can have. So in other words, I want to maximize my area. So my optimization is going to be the area of the rectangle, which we know is just going to be base times height. So I need to write a model for area, base times height, of that specific rectangle. A rectangle that is inscribed, in other words, these corners are touching the curve under this sine curve. And the way we're going to do that is by defining base and height in terms of this sine curve and how they relate. Okay, so first things first, the height is probably the easiest thing to define, because when you have a curve that is inscribed, or when you have a shape that is inscribed, we know that this distance right here, the height, has to be the height of the curve at that point. It doesn't matter where I put my rectangle. If I make my rectangle low like this, the height of it is still going to be determined by that sine graph. If I make my rectangle be up high like this, its height is still, determined by the sine graph. So for my height, that is literally just the height of your graph at that point, right? So I can call my height, I'm calling it sine x. Right? So that means that I'm calling this distance right here x. So if that distance right there is x, then if you go over to x and go up to the curve, that y value at that point, that's the height of my rectangle. The height of the curve. So no matter where, and again, I could have there's a ton of different possibilities for rectangles here. We don't have to use the one that's in the picture. I could draw my rectangle tall and thin, and still I'm going to say, okay, the distance over to my rectangle is my x value. So sine of x is the height of my rectangle. Okay, so that's how I'm defining my height. Now, that means that I also need to define the base, or this distance, in terms of x. Okay, and again, x being the way we defined it, the distance between 0, or the beginning of the sine curve, regardless of which arc it is, and the edge of my rectangle. So we have to use symmetry here. This is x, right? Well, if this is x, then guess what? This distance over here is x as well. So that leaves me with this as my base. And again, we know, since this is a sine curve, that this whole big distance here has to be pi. And I just happen to be teaching segment addition in geometry right now, and this is a beautiful example of how you apply geometry when you're doing other things. So here's what I know. I know that this x and this base and this x must add up to pi, right? So I have two x's and a base that have to add up to pi. Segment addition postulate. So my base must be pi minus 2x. And there we have it. Now look, restriction. The restriction is that it was inscribed under sine x. So it's not that we had to write a separate equation for the restriction. We kind of handled it already, right? When we defined our base and our height, we used that fact in order to create both of these. So now if I want to maximize my area, I just take my pi minus 2x times my sine x and maximize it, take my derivative. I don't have a choice here. I have to use the product rule. So we'll optimize. So let's see, I'm going to have a pi minus 2x times a cosine of x. I'm going to have a negative 2 times sine x, and I need that to be 0. Now, I don't know about you, but I'm pretty sure that algebraically we can't solve that. So I am going to put that in my calculator. So I'm going to graph pi minus 2x times the cosine of x minus 2 sine x. Get a graph of it, because that's my derivative, and see where that derivative equals 0. And again, I'm on the interval from 0 to pi. So if you look at the whole graph, it's got lots of dip-de-dips and curves, right? But I only want to be on the interval from 0 to pi. So I'm going to go onto my window and say x min and x max from 0 to pi. And when I graph it then, I only see 2 zeros. All right, so looks like a stretched out parabola a little bit. So if I calculate my 0, it's somewhere between 0 and pi over 2, let's say. I find a 0 at 0.7104627. So 7104627. So I'm going to call it 0.710. That means this distance is 0.710. Right. So the other 0 that you are seeing is when x is that. So if you look at the graph of your derivative on the interval from 0 to pi, you're going to see 2 zeros. One is here and one is here. Okay. But if your x is this, it's going to bring you to that point, but it's not going to be, you're going to have a 0 area at that point because you won't be able to inscribe. All right. So what did it ask? What are the dimensions given that area? Okay, so this is solidly not my answer, right? This is only this 0.710. If I want the dimensions of my actual rectangle, it's going to have a height of sine of 0.710, and it's going to have a base of pi minus 2 times 0.710. Okay? Because if this is 0.710, then this is 0.710, which means this is pi minus 2 of those, and then this is just sine of x. So the answer here, they wanted the dimensions. We need to give them. Okay. Notice they didn't give units in this problem. We're not giving units back in our answer, but x only gets you so far. You have to pay attention to what they asked you in the question. So again, this is a I call this constructing in 2D because you're not folding up anything or creating a three-dimensional space, but or object. But we do see some problems like this, like I said, taking a paper and making margins and maximizing an area, or we see ones, and I believe there's one in the stations where there's two buildings, and for some reason you're there's like a cable that connects down to the two buildings or something. So there are some two-dimensional construction problems. But again, you're always looking for what am I optimizing and what's my restriction. There's no two questions alike when it comes to optimization problems. It's just a matter of getting used to kind of piecing them apart. What am I trying to maximize or minimize, and what restriction do I need to make sure is incorporated into that model before I take a derivative? Okay, I look forward to filming another video for you. I'll see you soon.